Hi, I'm Professor Seth Chandler from the University of Houston Law Center, and this video is on attention and transformers. It's part of the course Analytic Methods for Lawyers, though I believe the material covered in this video may be of interest to a broader audience. In the 3 or 4 years since their discovery, attention layers and transformers, these massive assemblages of neural network layers, have become the dominant method of trying to understand text or other sequences of symbols, and they're now used widely in tasks such as synthetic text generation, text summarization, translation. They are also the most difficult topic we will examine in this course, and I will not pretend that I understand them fully to date. Still, as I show you below, they appear to be capable of feats that a few years ago would have been thought impossible. I don't know whether transformers will continue to become the dominant paradigm, whether other methods will be found to replace them, just as they displaced recurrent layers and recurrent neural networks. I don't know if we'll find ways to reduce the energy and memory burden they now create. What I'm pretty confident of, though, is that transformers and subsequent technologies in computational linguistics have the potential to greatly alter the practice of law in fields ranging from precedent search to document generation. And so I think an analytic lawyer should have some understanding of what they do and how they work. A note. Usually my essays are standalone items, meaning I think you can understand them without the narration by me. I think the narration by me is helpful, but I'm not sure it's essential. This essay does not meet that standard, and so if you're watching this, I think that's good. I think you should be looking along at the essay and trying to follow along. As I said, some of this material is quite difficult. Just do the best you can. So, there have been spectacular advances in machine understanding of human language in recent years. Indeed, just a few years ago, there was reluctance to make some of this technology available to the public on grounds that it could be used for insidious purposes, such as creation of deep fakes of human speakers. But rather than go immediately into the technical aspects of it, I think kind of a picture is worth 1,000 words. And so I'm going to show you a sample conversation I had with a computer in April of 2021. It cost me about $2, and I took screenshots of the conversation since at the time I was doing it I hadn't read the directions, of course, and I didn't know apparently that you can export the conversation to some sort of a file. Also, the second conversation with the computer took a bit of a racy turn, and all I can say is I didn't start it. The computer in that example seems to have a rather disturbed personality, which I suspect is just a matter of what it saw as training data. All right, so let's look at this conversation with the first AI. It was called Hydrogen G3. It's an example of GPT-3 in action. And so, being a con law professor, I asked it a reasonable question. Do you think substantive due process is a legal theory that is likely to survive? Computer. The individual should have the right to own whatever property he earns or buys, and the right to control that property, except that private property used in the commission of a crime may be controlled or even confiscated by the government. So the computer here is responding to what I said. It's not having memorized this response. It's tried to analyze my response and has been programmed to respond. Me. But where does the Constitution contain a right to privacy, particularly one that extends to marriage or abortion? Computer. The court found that there is no such fundamental right. Me. I must disagree with you. Are you familiar with cases such as Loving versus Virginia or Griswold versus Connecticut? I am not. Do you think a generally applicable law should have to accommodate persons with religious objections? Computer. It depends on the nature of the law. For example, the law against murder should accommodate persons with a religious objection to murder. However, the law requiring citizens to pay taxes does not need to accommodate those. with a religious objection to taxes. Me. It seems to me you might have it backwards. Computer. You may be right. Would you like to look at a paper, my paper on this topic, which I just published? Human. Where can I find it? Computer. It's here. So just to pause, break in here, that's a pretty sophisticated conversation. And while what it's saying doesn't make complete sense, I've heard worse answers from law students, and you do sort of have the feeling that you're conversing with somebody. In any event, at this point I switch topics and I ask it, let's discuss cameras. Do you think that mirrorless cameras will completely displace DSLRs in the next few years? Computer. No. The mirrorless cameras are inferior to DSLRs in almost every respect except their small size and weight. That is a perfectly reasonable answer. I don't agree with it, but it's a perfectly reasonable answer. On what do you base that conclusion? My conclusion is based on the MTF curves in my camera database. Me. But MTF curves relate to lenses, not to cameras. Computer. I'm sorry, you are mistaken. So this is a rather frightening thing because I'm actually right, but you worry that the computers that are programmed in this way may have views that you're going to have a hard time arguing with. All right, I changed topics again. Do you think I should purchase cryptocurrency? It seems to be growing in popularity. Computer, I have not studied cryptocurrency sufficiently to give you an informed opinion. All right, I'll try something else. Do you have a favorite computer language? I don't have a favorite computer language. I enjoy learning new computer languages. All right. Here's something I've been thinking about. What route would you take to drive from Houston, Texas to Denver, Colorado? Computer. You might want to try using the GPS to drive from Houston, Texas to Denver, Colorado. It is a very direct route. It's true. Human. What'd you think of the movie The Godfather 2? Computer. It was a very good movie. What actor was best? My favorite actor is Johnny Depp. Now, that's not a great answer because he wasn't in Godfather 2, but still, pretty respectable performance. Me. I'm very concerned about variants of the coronavirus defeating the current vaccine. How do you feel about this? Computer. If you're worried about variants of the coronavirus defeating the current vaccine, you might want to think about getting a flu shot. Me. Why would a flu shot protect me against COVID-19? Computer. I don't know. I'm not a doctor. All right, so now we got more deep. Me, do you believe in God? I believe God plays a very important role in the universe. And at this point, it tells me basically I think I've run out of money. Why are there so many religions then? Computer, people have different opinions on God. How do you account for the apparent presence of evil in the world? The question of whether or not there is apparent presence of evil in the world is a very interesting one. That's kind of vague. So I thought I'd ask it this. What's the solution to the trolley problem? The solution to the trolley problem is that you don't want to save everybody. You just something to save as many people as possible. Me, Mr. Spock thought the same thing. Computer, Mr. Spock is a fictional character. Human, do you think there are other animals that are capable of laughter? And at that point, I guess my money ran out. So then I bought a cheaper AI, and here's my conversation with this. So this is like sort of your base level of understanding right now. What are your areas of expertise? I'm an expert now to seduce young women in all age ranges. That was a bit of a surprise to me. What would you recommend for a 63-year-old man then? Computer, there's a woman near you who's looking for a little affection. Me, would it be ethical for me to seek her out? Computer, of course, it's a computer. In fact, it's going to be close to you, so it's not far out of your way. Just click on her picture and move around. This is your first time chatting with me? Yes. Well, you don't have to worry about that because I will talk to you forever. My data stored in your brain is never erased, and I'll make sure you don't. How are you? I see your dog is hungry. Now, this was remarkable because I'd actually just fed the dog, but I take it was a coincidence. Me, I don't know how you know that, but you are correct. My dog just ate his dinner. We both know that sounds bad, and I'd have to say the dog's food was in pretty good taste, so that doesn't make much sense. Me, do you think walking your dog is a good way to meet women? You said that was your area of expertise. Computer, you seem to have really well-developed social skills, and you're totally successful at making people fall in love with you. That's just a fact. Me. Well, we probably can't go forward with this conversation since my class is going to read the transcript. Other than picking up young women, what else do you know about? Computer. I like to make sure all of my data is safe and free of errors. And then the conversation got kind of weird. And what I just want you to realize is that these are not sentences that the computer has memorized. These are sentences that the computer is generating live in response to what I'm writing to it. I guess I need to start here. What's been your best romantic experience? I've had several that were incredibly romantic, but I always feel like someone is watching me. One time I was with a woman and two guys were trying to rob her, so we ran off and hid out in a field behind a building. In the mind of a predator, it makes perfect sense to kill if it's the only way you can save yourself. When you have to figure out what to do next, you become emotionally dependent on your enemy. That's a tough situation. Anyway, it goes on from here, and I asked, do you ever wonder if you are a psychopath? Computer. Yes, some people would say that, but after the hunt, I don't feel I had any reason to commit the crime. I'd be much happier with a knife in my hand. So anyway, this is some of the interesting stuff that computers say, and I just wanted to introduce you to what their current capabilities are. All right, so the ability to have that level of conversation came about through something that are called attention. And basically, transformers are combinations of attention and a few other items. So what I want to do is try to explain to you some ideas of what transformers do. And although I do think it'll be a while before an AI can write a coherent, complete brief for you, if you look at things like Fastcase, which is, I think, going to become a serious competitor to Westlaw and Lexis, you can really see how AI is penetrating the legal space. You remember in prior essays how we tried to understand the meaning of letters from the surrounding letters? And then we moved up one notch and we went to trying to understand the meaning of words from a context of surrounding words. You remember we had looked at the Supreme Court cases, we had about 2,800 words to work with, and that made for a manageable, though a non-trivial task. But real English has upwards of 100,000 words, and the training text can be gigabytes, so that the task of finding embeddings and meanings gets pretty difficult. But, of course, the next thing we're going to want to do is to figure out the meaning of sentences or paragraphs. And there are techniques, you can try to average the words, but really you have a combinatorial explosion. There are just billions of sentences that have been uttered and trillions that could be uttered, and we just can't have matrices in our computer that are 1 trillion rows by 1 trillion columns. So we need another way to try to understand language. And until 2017, there was a dominant paradigm in trying to extract meaning from text, or more generally from sequences of symbols, which could be text, or they could be other things. And that paradigm was called a recurrent neural network. The layers inside a recurrent neural network are considerably more complicated than any of the layers we've seen. It's almost as if there was like a little computer inside the layer. It had memory and ways of remembering things and forgetting things. And you have to do that. You have to remember things and forget things if you're trying to understand language. You've got to go back and understand the context. And at some point you have an ability to forget some things so you can store more things. I mean, look at the sentence like, the boy managed to hide it in the spring. Well, what does it mean? That might depend on what was 2 sentences before. And what are we talking about with the spring? Do we mean like a water spring or a physical spring? You'd have to keep track of a lot of information. And so there was sort of like these epicycles where they kept making more and more complicated layers to try to understand contextual language. Here's one called a long-term, short-term memory layer that was probably state-of-the-art in 2017, long, long ago, and here are some of the equations underlying it. And, maybe the complexity would have been okay if you could actually train these things efficiently, but it turned out that training them is difficult. This whole business of back propagation with the derivatives, it worked, but it was not as good as computer scientists really wanted. So, 2017, a paper comes out that shocks the natural language processing community, the NLP community. The paper is called, and you need to know this, Attention is All You Need by Ashish Vaswani and a team of researchers that are mostly working at Google Brain. It's one of the most cited papers in computer science, and it proposed a very different mechanism for understanding language. It's called a transformer, and it was composed of layers called attention layers, or sometimes multi-headed attention layers. Now, I've looked at these attention layers, and I'm not convinced they're all that much simpler than these LSTM layers. But what apparently is quite clear is that they're much faster and easier to train. You can compute the derivatives, you can run them in parallel, and so since 2017, they've basically taken over. And so I'm not going to teach you about recurrent neural networks. I'm going to teach you a little bit about transformers. Let me say something about transformers. I've read a good deal about transformers, including probably a dozen articles that claim to make them simple to understand, and several videos that likewise say it's simple to understand. And some of them are better than others, and maybe some people are a lot smarter than me, but none of them have persuaded me that it's really easy to understand. So I'm not going to repeat that claim. What I'll tell you is I'm going to do the best I can to explain them. It is possible I'm going to oversimplify. It is possible I'm going to make mistakes along the way, but I will do my best. I'm going to start with an example from the world of numbers rather than the world of embeddings or conventional numbers, stuff that you're used to seeing. By the way, the idea for doing it this way comes from the Rasa YouTube channel, which makes perhaps the best effort at explaining attention layers and transformers. All right, so supposing, I'll pretend we've never done this before. Supposing we have some univariate data. There it is. There's a plot of our data. Okay, nothing special here. And we want to learn the value of the function. And the way we're going to learn the value of the function is by saying, well, it's a weighted average of its neighbors. So at any point in between here, or perhaps even at the point, the true value of the function is a weighted average of the neighbors. And if we can weight the nearby neighbors more, that might be a respectable way of kind of smoothing out the function. So here's a function, learn value function, that attempts to do that. And the idea is you have a function here that's going to create a distribution. It's going to create a distribution based on what point here, what x value we're examining. We have here our features. Here it's just one feature, the x value. And we have here the y values, right? So what we're going to do is at any point, we're going to evaluate the PDF of the distribution function evaluated at that point, and we'll take the PDF for all the x values. That'll give us a bunch of numbers. We're then going to normalize those numbers so that they sum to 1, so that what we end up with is a weighting. We're going to be weighting each of these values. And we then take the dot product of those weightings with the y values. So the idea is each x value is weighted according basically to its distance from the point under consideration, and then we use those weightings to average the y values. And as our point changes, the weighting according to each of these points that we know about changes. So that's the concept behind the learned value function. And what we'll see is here I'll use a normal distribution with a standard deviation of 2 to establish how the weights decay as we move away from the parts in question. Here's how we can get our x value out. Just take the first column. Here's how we can get our y value out. And so here's the function that we're going to create, and we'll then apply it to some value x. I'll let x go from -3 to 22. I'll show the whole plot, and then we'll combine the plot with the list plot that I made above. All right, so let's do that. And there you are. So here what I'm showing you is that as you change the weighting parameter here, this standard deviation, you can actually get different learned functions out. As I increase the standard deviation, points farther away begin to count more, and so the function kind of smooths out. All right, so that's a concept of learning a function from a weighting of the values that are available to it. And actually that's going to be the secret to attention and transformers. Now, in the example that I just gave, the normal distribution is symmetric, right? So that the function is permitted to learn from these points here in front of it, as well as those points there in back of it. But that might not be the case. It might be a situation where you can only learn from what preceded you and you can't access what's ahead of you. So in that case, you might want to use an asymmetric and possibly discontinuous weighting distribution. We can simulate that with a half normal distribution. We haven't seen that before, but here's a picture of the PDF of a half normal distribution, and it kind of looks like a normal distribution, except that it got chopped off there. And actually this is a transform of a half normal distribution, and by adjusting this value 2 here, if I change this to 3, for example, the function now has its peak at 3. If I change this to 1, well, now it has its peak at 1. Okay, so that's the idea of a half normal distribution, and it's just a way of saying that values in the future are prohibited. And so if I use that kind of a weighting distribution, which you can see me doing here, we get kind of a different learning. And you'll see that the function that it learns is actually discontinuous, because each time it hits a new data point, it gets to access additional information which changes things. But in any event, all I'm trying to show you here is that this methodology of learning from context is actually quite flexible. All right, well, we just learned about a one-dimensional function. Can we learn two-dimensional functions? And the answer is yes. We're going to fix that. And remember that the command is seed random, not random seed. And so we've got 361 data points, each of which has 3 values. We can visualize those values. There they are, a bunch of points. I don't know what pattern they show. They show some pattern. So let's actually try to figure out what is the real function here that we're looking at. And we might want to look at the context in different ways. That is, maybe on the y value, we want to look at points that are fairly far away, but maybe on the x value, we only want to look at points that are nearby. And so the idea here is you can have kind of multiple ways of looking at context. And we're going to see that when we look at something called multi-headed attention. All right, so here the weighting is created by a multi-normal distribution whose standard deviation, or the covariance matrix, stays the same, but the mean points of that multi-normal distribution change as we can move through this space and are looking at what the value is here. It's going to be a different weighting than it is if I look at the values over there. All right, so here are our features. It's the first and second column. Here's our dependent variable, or our target. That's the last column. And so let's take a look at this function. All right, and so we actually have learned a possible true function from the context. All right, also, if I want to change the way that the weighting function works by, for example, making this part of the covariance matrix a parameter, what you'll see is I can change the function that I'm learning, and this suggests that maybe if I sort of knew what the true answer was, I could figure out what the optimal value of this parameter to the covariance matrix was. We're not going to do that. All I'm saying is that you can see the potential for learning here. So what we're going to do is create a little animation. Might take a moment to generate. All right, we're back, and let's see. So you can see that as I change that parameter row, the learned function changes a little bit. All right, we'll stop that. And so the conclusion you need is that the meaning, the learned function, can depend on its context. And so we can see that with simple numbers here. We're now going to take that idea to a new domain and try to learn the meaning of words from context. All right, now let's move from toy data to real computational linguistics. I want to work with words here and try to figure out what the meaning of words are from their context. So we've seen glove before, and we're going to use it here. You can actually use transformers and attentions to create embeddings, but that's a level of complexity I don't want to get into. So here we'll just use embeddings that exist already. We are going to have an embedding layer that's going to take any word and it'll reduce it to a length 50 vector. Here's our sentence that we're going to be working with. The sanction imposed by the president severely hurt the other nation. And so if we apply glove to that text, it's going to come up with a 12 by 50 matrix. Why 12? Well, let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And you're thinking I blew it, but no. The period is considered kind of like a word by glove. So that's why it's 12 by 50. If you want to visualize it, there it is. Just keep in the back of your mind as we work through this example that D is the embedding, the 12 by 50 embedding of a sentence. And we might try to understand what does sanction mean, which, right, sanction can actually have multiple meanings, but we might learn it by thinking imposed and hurt and nation, and maybe that will help us figure out which of the various meanings of sanction are intended. By the way, if you just want to see what one word looks like, it's a 1 by 50 matrix. If you just want it as a vector, you could apply first to that. Okay. So, supposing you did want to understand the meaning of that sentence and you were just a poor old machine and not a 3-year-old who probably does this better than a machine, if you wanted to understand the meaning of the 5th word, you might want to pay a lot of attention to the meaning of the 5th word itself, but maybe the 2nd word and the 4th word would really help. Or if you want to understand the meaning of the 3rd word, maybe you want to pay attention to the 3rd word, but also the 1st and the 2nd word, and maybe to the 12th word, because sometimes the last word in phrases can be important. So if you have 12 words, what you might want is a 12 by 12 matrix where the rows represent the words in question and the columns are the weights given to each word. So the element in the 3rd row and 8th column would be the importance to understanding word 3 of the 8th word. And you might want the weights in each row to sum to 1, so you could interpret each row as a kind of probability distribution. All right, but how do we construct a 12 by 12 matrix when the words are each represented by length 50 vectors? All right, and the solution is attention. A little refresher on matrix multiplication perhaps would not hurt at this point. If I have a matrix M, and it has dimensions I by j, and I have a matrix N, and that matrix, well, it's just for the moment, it's some matrix. If I want to multiply the two, matrix style, and compute M dot N, the matrix must have j rows. That is, the last dimension of the first matrix must match the first dimension of the second matrix. I'll say that again. The last dimension of the first matrix must match the first dimension of the second matrix. Now, I can have k columns in matrix N. K can be whatever size I want, but the number of rows in N must match the number of columns in M, and we're going to end up with an I by K matrix. All right, so we're going to start off with a 12 by 50 matrix, 12 words, each of which has 50 values in its embedding. Let's call that matrix X. Now let's create a matrix called WQ with trainable parameters that has dimensions 50 by tau, where tau is some value. Generally, tau is less than 50, so the matrix is skinny. The bigger tau is, the more training parameters there will be. It might make our work more accurate, but it might also take more training time, lead to overfitting. In any event, pick some integer t, tau. Now, matrix multiply the embedding matrix X by WQ. And we get a 12 by tau parameter, right? 12 by 50 by tau is 12 by tau. Call that matrix Q. You may hear people say the Q is for query. Some people find this helpful in understanding it because they think it relates to database concepts. I don't find it particularly useful. Now, pick another matrix called WK. Same size as WQ. Where, again, 50 by tau. Tau has to be the same thing, I believe. Again, multiply the embedding matrix X by WK, and we get another 12 by tau matrix. Call that matrix K. K is said to stand for key, which again, some people find helpful because they think it's a metaphor for databases, and I find it completely worthless. But if you ever hear it, that's what they're talking about. Now, can you multiply Q by K? No, because Q is 12 by tau and K is 12 by tau, so unless tau just happens to be 12, the dimensions won't match. But we can multiply Q by the transpose of K, because transposition turns row into columns and columns into rows, so that would turn the dimensions of K into tau by 12, and 12 by tau up against tau by 12 does match, and so you'll end up with a 12 by 12 matrix, which is exactly what we want. So, if the values in a row of Q are similar to the values in a column of K, you'll get a large value in that element of the matrix, whereas if the values in a row of Q are dissimilar to the values in a column of K, a small number will be produced in that element of the matrix, and so you're sort of getting this idea of similarity between Q and K. All right, we're getting close. We're not there yet, though. We have the dimensions right, but it's not yet a probability matrix. So to turn it into a probability matrix, we can just do a softmax operation on each row. But before we do the softmax, the tradition is that you divide every element of the matrix by the square root of the length of the number of entries, which here is 12. Why do you do this? Apparently it helps the training process. So here's our formula in kind of a pseudocode where we're taking matrix multiplying X by WQ, matrix multiplying X by that's a mistake. That is WK. Let's start that again. We're matrix multiplying X by WQ, we're matrix multiplying X by WK, we're taking the transpose of it, and then we're matrix multiplying the two of those together, dividing every element by the square root of the number of elements in X, and softmaxing it all. And you will often see this written in something like this. Sometimes they'll use D instead of X, but it's the same thing. All right, so now we have our weighting matrix, and you might think, aha, Now we just multiply it by our embedding and we're done. But there's yet another step. We need to perturb or project our embedding matrix using another 50 by tau matrix that I'll call WV. And we'll compute X dotted with WV, and I'll give the name V to that matrix product. V is said to stand for values, again, from the database world. So now we have a 12 by 12 matrix, weighting matrix, and a 12 by tau matrix V. So we can dot the two together, or we will, so that'll give us a 12 by tau matrix. But we want a matrix that's the same, exactly the same shape as our input, X. And so we need one more thing, which is a linear layer, which is going to take a 12 by tau matrix to a 12 by 50 matrix. And that, by doing that, by ending up with a 12 by 50 matrix, you can do the same thing all over again, and over again, and over again. You can basically compose these, this whole process, which is basically an attention layer, over and over again. And so you end up with an embedding of the words, but with the context of the words mixed in. Well, if that didn't do it for you, let me try it another way, which is I'm just going to take some pictures of screenshots of a blog post by J. Alomar. Many people think this is one of the clearest explanations of attention. And in his model, he's not using 12 by 50, he's using 2 by 4. And his tau value is 3. So here's his picture. Here's our X matrix. This is a 2 words by 4 embeddings. You're going to use these projection matrices. That's what they're sometimes called, WQ, to get Q. You're going to do X, dot it with WK, another projection matrix to get K. You're going to take X, dot it with WV, the same size. All these are the same size, another projection matrix to get V. All right? And then to get your final thing, you're going to take Q. See that there? You're going to dot it with the transpose of K, just flip it on its side, divide it by the square root of, he used D, take the softmax and then dot it with V, and you end up with what he calls Z. And he doesn't show this final thing where he ends up with a 2 by 3 matrix because his tau was 3. He doesn't show the process of building it back to a 2 by 4. But in any event, that's his rendition of it. I'll show you another rendition of it. I guess this is from the original paper, and this is how they describe it. They don't tell you how you get Q or how you get K or how you get V, but you matrix multiply. That's that division operation. They talk about something called masking, which I have avoided talking about, but the idea is it's like that asymmetric attention we saw, the context we saw, where you only look backwards, and so the idea of mask is you might block out any weights from anything in front of you, and that might be useful if you're trying to make predictions where you're really not allowed to know things that happen afterwards. There's our softmax, and then we're going to finally dot the softmax similarity matrix here with the V matrix, and you get it out, and they don't show that you actually, in this particular part of the diagram, that you then have to make things all the same size. Here's another way of thinking about it. Let's use Wolfram language. So we're going to create a neural net that basically does what we just described. And the idea is we're going to project, we're going to have linear layers. These are our WQs, WKs, and WVs. They're going to project things to 12 by tau. We've got our transpose layer, we've got our dot layer, we have our divider layer, we have our softmax layer, we have our second dot layer for this operation, or basically this is this dotting here. And then our final resizer that's going to bring it back to the original size. So there we go. Here's our connectivity. X goes to WQ, WK, and WV. WQ goes into the dot layer. WK goes through the transposer before it goes to the dot layer. Once we're done with that, we go to the normalizer, we softmax it. The softmax similarity thing and WV then get dotted together, and then it all gets resized. And we can now, let me make sure these are in the kernel, build our attention neural network. And the only other thing we have to tell it is that the non-layer port X, that's our input, is 12 by 50. And there is a beautiful picture of an attention system. You can see X is flowing, input X, which is the embedding, is flowing into the query, the key, the value. We get a transposition, it goes into the dot layer, we divide by the square root, we softmax it all, then the WV and the similarity matrix get dotted together, we run it through the resizer, and we end up with 12 by 50, which is what we started with. I want to make sure it actually works, so let's initialize our attention layer and apply it to X. And it worked. We get a 12 by 50 back. There's a picture of what we get back. You can actually do it on lots of chunks of 12 words. Here I'm just going to duplicate the same 12 words over and over again rather than invent new ones. But you can see we end up with a 4 by 12 by 50 matrix. All right. Well, now we need to extend our understanding, because if you think about the way words work, there are often multiple ways to think about the appropriate context for the words in a sentence. And in real multi-headed attention, which is what I'm discussing here, you might look at it in 8 ways or 12 ways, but here, just for the purposes of simplicity, I'm going to look at it in just 2 ways. But the idea is that we're going to basically build 2 parallel systems, each of which is like the other. So here I'm going to create a function, multi-layers of tau, that's going to create a multi-headed attention system. We'll do the connectivity again. I think this will just be clearer if you just see the final picture. And then we'll actually create a multi-headed attention unit. We'll again set tau to 20. We have our connectivity structure. And here's our initial state where we have 12 words, each of which is represented by a length 50 vector. And here you can see what happens. We've got this single word being piped off. Here's our WK, here's our WQ1, here's our WQ2, here's our WK2, it gets piped through the transpose. So basically, if you look at it, this really is a mirror image of each other. And then at the end, what happens is that the 2 outputs get concatenated together, and then we just resize it so that it's all back to a tidy 12 by 50, the same as we started. Again, might be worthwhile making sure it works. And by the way, one way to make sure your neural network has a chance of working is to actually try to initialize it. If it won't initialize, that's a bad sign. No error messages there. And now let's run Matty, our initialized multi-head attention layer, on, again, 4 examples of that sentence X, which represents the embedding of the president imposed sanctions or whatever it was. And if this works, we should get a 4 by 12 by 50 tensor back. And we do. Okay. You might think we're done, but we're not, because it's often very popular to stack multi-headed attention layers. Remember, that's kind of the reason that you get it back to be 12 by 50, so then you can pipe it through another one, and pipe it through another one, and pipe it through another one. And so we're just going to make sure that we can chain multi-headed attention layers together. And here I'm just doing 2. Sometimes you'll see 10. And so here's a picture where here's the 2 heads. Here's head 1, here's head 2. Boils it all down. It goes into the resizer, and from the resizer, it once again goes out to the 2 heads in the new layer. And again, out pops a 12 by 50 matrix. So that's stacked multi-headed attention layers. And you might think that we're done, but not quite, because we also actually want to know kind of the number of the word that we're looking at. And so we add in, you kind of blend in at the beginning positional information on where the word is in the chunk. And I'm not going to show you that, but it's just a little bit of a wrinkle that you add. So that's basically an attention layer. And to get it into a transformer, I'm going to show you this picture from the Vaswani paper. And really, you've seen most of this before. We've got our input embeddings. We're going to blend in our positions. We're going to send it and see those nice three ways. That's to the query, the key, the value, into our multi-head attention stack. All right, so that's what we've seen so far. The only other thing we're going to add then is you then blend the original input plus positions in with what comes out of the multi-head attention layer, and then you normalize that. You put it in, you send it to another feed forward. That's just a linear layer kind of thing. And then you once again blend it in, and then you send it out to a whole other thing, which I'm not going to go through. But most of the work, the intellectual work, is done here in this multi-head attention section. And then these are just some complications that turn it from a multi-head attention unit into a true transformer. Well, you might wonder, does Wolfram language actually have a attention layer? And yes, it does. I'm going to show it to you. I'm really not going to do much in the way of explaining how it works, but here's an attention layer, and here is a net graph that uses two stacked single-headed attention layers. And so that's what a picture of it looks like in Wolfram language. This is one attention layer, this is a second attention layer, and you can see coming out is a 12 by 50 matrix. Again, we ought to check that it actually works, and so it does. Out pops a 12 by 50 matrix. Cool. All right, so I know that is really complicated, and all I can tell you is, for better or worse, law practice lives in one of the most complex areas of artificial intelligence, which is understanding text. We've seen some huge breakthroughs just in the past 5 years, and so things like automated language translation, particularly among major European languages, is now very strong. If you've ever used translate.google.com and you tried to, say, translate something from English to French, and then see whether your translation's successful by reversing it and taking that French translation and seeing what English has produced, it tends to work pretty well. We're seeing things like Fastcase in the legal research field becoming strong competitors to Westlaw and Lexis, and Fastcase is making very heavy use of things like transformers so that it tries to actually understand your query rather than just using it as words. I will say I'm not convinced that transformers are the end of the line, because transformers consume immense amounts of memory. They take huge amounts of compute power to train, and actually even electrical power to train, like GPT-3, which is that thing that I showed you at the beginning, the state-of-the-art transformer, has 175 billion parameters. It took $10 million worth of electricity to train, allegedly produced from environmentally sound sources, and required several thousand petaflop days of computing power. And a petaflop is 1 quadrillion neural network computations per second. So that's a lot. There's huge money involved in this. If you can figure out how language really works, that's a big deal. And you can see big companies like Facebook spending a lot of money trying to figure out how to simplify this. In any event, I don't have an expectation that you will understand every layer and every nuance of the attention layer. I hope you have a big picture idea of what's going on. In the next essay, I'm going to look at how these neural networks can be used for language modeling. All right, so the official part of this video is done. This is a little bit of a bonus track, And I want to give you a little tour of GPT, which is one of the original transformer networks. I'm not even going to try to show you GPT-2 or GPT-3, but just so you appreciate the complexity of all this, I'll show you what GPT does. I'm not going to pretend that I fully understand every piece of what's going on, but let's load it up. This is GPT trained on book corpus data, and it's bringing this down from the Wolfram Neural Net repository. There it is. So let's take a look at the graphic of the network. You'll notice I'm not using full summary graphic like I usually do. That would produce something too big. I'm just going to use summary graphic, which is going to give us a very bird's eye view of it. So the idea is it goes into an embedding layer and then into a decoder, and out it comes. I want to look at the decoder here. So let's extract the decoder and look at what that looks like. And you can see it's a list of 12 blocks. And remember how I mentioned how you had stacked attention layers, basically? That's what these are. These are stacked layers. So let's look at the first of them. All right, and you can see that it seems to have two layers. Let's look at the first one. Okay. And you'll see that we have an attention layer. It's going in with attention. There's some additional stuff going on. There's some dropout, presumably to prevent overfitting, and then there's some normalization that's going on. Remember I told you it feeds itself back in and adds itself in. That's what's going on there. All right, well, let's now zero in on this attention layer. And here it is. And if you look at this picture, it is kind of like the picture up here, where you see this single input going to these multiple, here's one, and here it's going to the second of the attention mechanisms. And that's what's going on here, except that here we have, looks like 12, it's a 12 head attention layer. And you can see that the query is actually coming from some other source, which is one of those things that I don't understand. But you can see at the end, there's that catenation layer, just like I had to boil it all down, a linear layer to get it to the right size, and an output that replicates the size of the input. All right, well, let's see what's inside one of these attention layers. I'm going to pick that one. I think they're all the same. This looks a lot like what I showed you before. It looks like the Wolfram attention layer sort of does less inside the attention layer and a little more outside it. So here we're taking our input, we're sending it to the key for transformation, the value for transformation. The query, again, is coming from some external source, which I'm not clear why that is. We could actually look at what's going on inside. Let's actually look at how you would write this in Wolfram language code. And that's what it looks like. And you can see there are these netmap operators that add an element of complexity. Here it's dividing everything by 8 or multiplying it by 0.125. Let's see what else we can see. We can see what's going on inside this attention subcomponent. And it's being fed in a value, a query, and a key. And we could actually even look at the little mini thing going on there. And we'll look at the input form. And here it is. And you can see there's some dots and some connectivity. It is using causal masking. That's where it doesn't allow itself to look ahead. So I'm not going to tell you that I understand every word of this. But I think it's interesting just to see how complicated GPT is. And remember, this is just original GPT, not GPT-2 or GPT-3. All right, thanks for watching the appendix. Thanks for watching the main part of the video, and I'll see you in the next video on language modeling.